Hello all, welcome once again to the maze magic room of statistics. It's a pleasure to have you here. Virtual though our space is, the meaning and the value of the material is endless and very, very tangible. So allow me to walk you through the beginning of this, Unit 4, which is random variables. Random variables being variables we don't really know how to denote, so quite often we denote them with x. And then of course p of x would be our probability of x. And so anytime we go to make a probability model and map out a sample space, we might go through and for every conceivable probability, we'll state the events / outcomes known as x. And then the probabilities attached to those outcomes, which will be p of x. Now, if you would, go ahead and pull up your slideshow alongside me, 4.1. And you'll see that on slide 5, it says discrete and continuous random variables, right? Now, some of these are old school terms, old hat, stuff you've seen before, stuff that shouldn't be too confusing. But let me walk you through real quick. So on slide 6, we have our definitions. We have discrete, and then we, of course, have continuous. Now, I really like the way I've gone ahead and defined these two terms for you here. They're both, of course, kinds of quantitative variables, right? Which means they must be numbers. And not just numbers, because mind you, zip codes are numbers, but those are categorical variables, right? Because they denote something that can't be mathematically determined, right? You can't add and subtract or multiply and divide zip codes in any meaningful way. But quantitative variables, you can always add, subtract, multiply, divide in meaningful ways. And that'll come back next set of video notes in 4.2, so keep that in the back of your head or as a feather in your cap, if you will. I have on a baseball cap right now myself, so anytime I make a hat reference, just be aware it's an orange, of course, because orange is the best color, North Face cap. Now, you should already have your definitions for discrete and continuous mapped out, but just to make them very, very clear, discrete variables take on what we call fixed values, right? What does that mean? That means every value in a discrete set of events, you can't have values between those values. So if I'm saying like number of dogs, as the joke goes, I think I made a class the same about humans or a joke the same, I should say, about humans in class, which is, you can't really have 0.75 dogs. Well, you can, but it's heavily illegal and probably happened in South Florida. Okay. On the other hand, continuous variables have infinite possible values. And what does this mean? Well, what it means is you can have partials. You can have 0.875 of something. For example, money, height, all of these things, length of things, right? Measurements. A lot of these things are time is another good one, right? That has an infinite subset of values because you can always go between different values an infinite number of times. Okay. Moving on to slide 7, you can see I have mapped out, just like I did up here at the top of my video notes, at the top of my note show over here. There's the value of x, and then there's the probability of those values. Now, ways that we often denote that or map it out, as you can see here, is that we'll write like P1, P2, all the way up until PK. And that's for the probabilities, right? And then for the values, we might do x1, x2, all the way up until x. Oh, not P. X, K. And K just means the final value. Good to know. Whereas on the other hand, if I say XI, right, or PI, this means like any given event. Or here, any given probability. Right? And all this is suggesting is, and I want you to get comfortable with this, different ways to notate variables when we don't exactly know what fills that slot, right? And the other thing that I note in this slide is that all of your probabilities, P1 plus P2, as you can see, I do it all the way up until PK. If you add all your total probabilities up, they should add up to 1. And all probabilities are between 0 and 1. Including 0 and 1. If we move on to slide 8, you can see I have you solve this out, what you'll do to figure out the probability of x equals 2, because mind you, alongside this notation, another thing you might write is like probability of x equals 1, or probability of x equals 2. That's the same as right, P1 or P2. And what you'll note here is that you have the probabilities for x equals 1, 3, 4, and 5. And we know that these are all the total probabilities event set. So you just subtract them all from 1, and that gives you your final value for x equals 2, right? Nothing too wild, nothing too crazy. I believe the value comes out to 0.13, so you might want to set that up in your notes. 0.13 is probability of x equals 2. And because we need to always write our probability notation, the way you would write that is probability of x equals 2 is equal to 0.13. Or you would write P2 equals 0.13. It then says to create a probability histogram. All you need to remember for that is just that your x-axis is going to be the grade on the exam. And as always, your y-axis will be the frequency, which in this case is the probability. And then part C here says what's the probability someone scored a 3 or higher on the exam. And all we're going to do is add the values for the probabilities for P equals 3, P equals 4, and P equals 5. If you add those all up together, it's 0.19 plus 0.35 plus 0.27, and that gives you 0.81. Hopefully you wrote that a lot prettier than I wrote it myself. But there you go. That should make sense. And again, in terms of notation, you might write probability that x is greater than or equal to 3 equals, and then you would set this up. Very important to have that notation because it plays into slide 9, where I talk through this notation. So for slide 9, it says, what's the probability x is greater than 3? If I want probability x is greater than 3, I would write this. And if I want probability x is less than 1, I would do probability x less than 1 equals. And then I would set those values. So be sure you can run those types of calculations, but also that you know the notation for them and you don't feel lost in doing that. All right, we're going to move forward. Let's swap out purple. I was talking, some big game about how much I love the color orange. Let's do some orange, shall we? Now we're going to talk about expected values, which we write as E of x. We also can write that as the mean of x in this standard sort of notation. And all of this is just what's called expected value. So anytime you see expected value, this is what we're looking for. It is the mean value, right? And it is also, so actually all of these are the same thing. And they are all summarized as, and it says this on slide 10, excuse me, a little burp there, the sum of all possible outcome times its probability of occurring. So, fancy way of noting that is the sum, sigma, of all possible outcomes, right? X to the I, right? Because I'm saying any given value, but it's the sum of all of any given values, times the probability that x equals, right, any given x value. And you add those all together, right? So, I map out on slide 11 exactly how you would do that for rolling a die, where all the events are independent, right? Every roll is different. All it comes out to is that E of x in that situation is equal to 1 times 1/6, because the probability is 1/6 of any given roll. And then 1 is the value of a 1, right? Plus 2 times 1/6, plus 3 times 1/6, plus 4 times 1/6, plus 5 times 1/6, plus 6 times 1/6. And that gives me a value of 3.5. And that should make brilliant sense when you take a look actually at part 2 where it says determine the probabilities. Because they're all equally weighted, it would make a uniform curve, right? So if I were to make this as a probability curve where this is P of x and this is x, it would literally just be uniform with this being 1/6 of the time. It would hit that for 1, 2, 3, 4, 5, and 6. That's the ugliest graph I've ever made. Please forgive my heinous artistic skills, a lack of acumen on my part. But you'll note that they're all uniform. And because of that, you can always guess that the mean will be right in the center of that, right? Just like on a normal curve. But in this case, instead of it being like approximately normally distributed, it's just uniformly distributed. And so from 1, going from the value of 1 up to 6, 3.5 is the very center if you set that up, right? And all we did was we took each expected value x, any given one of those, and then we multiplied it by the probability that x is occurring, right? We do that for all of them, and then we add them all up together. Okay, beautiful. Now you will note that this one for slide 11 is where all the probabilities are the same, so I end up just summing all the total outcomes and dividing by 6. But if there are different probabilities, you won't do it that way. All right, slide 12 just gives us a totally different notation. The key here is making sure you know that it's the same, right? I'm saying here, mean of x equals e of x equals x1 p1 plus x2 p2. It all means the same thing. The very important part of this slide is at the very bottom of slide 12 where I say interpretation. If someone were to ask you, interpret what you're doing when you find the mean expected value. So your interpretation of the mean expected value, and you can tell by how much time I'm taking on this. Know this. Know this for your test. Know this for posterity. Know this for the AP exam for sure, okay? If someone says, oh, solve for the expected value, and then you do it and they say, interpret that. Interpret means explain. And you will say something to the effect of, if we, and here it says perform this chance process. You would say, if we, right, insert thing here. In this case, it was like roll a die many times. Our average, wow, that is, guys, I think that may be the ugliest average maybe ever written, definitely ever written by me, which is saying something. Average outcome would be blah, whatever that is, right? If we roll a die, right? In fact, the more exact way to say this would be, this is for the slide 11 stuff, right? If we roll a six-sided die, many times. The more times you write many, the better. Just kidding, but why not? Our average outcome would be 3.5, right? That is what we are saying. Know this phrasing. You can phrase it slightly differently, but make sure you hit the main points. Know how to roll. Okay, slide 13. I have some more problems. All you have to do is solve for the expected outcome and then interpret the results. So give that a practice for number 13. And you should see your phrasing, I'll betray to you. Your phrasing should be something to the effect of, if we were to run this AP exam long term across many students who signed up for it, our average score would be a 3.64, I think is what comes out here. In fact, I'm certain, sorry, I'm taking a sip of vitamin water here. Sponsoring this video, no, I'm just playing. Okay, but could you imagine? No, we're getting there, guys. We're blowing up. Okay. Like I said, though, average outcome would be about 3.64. So there, I give you both answers for slide 13. 3.64 for D, and then E would be, if we, et cetera, et cetera. Okay, we're looking at slide 14, and it just says what's the expected outcome for a number of cars. You should calculate this on slide 15. I make it clear that the answer is B, 1.75. All you had to do was multiply the number of cars by each of the probabilities. Make sure to incorporate 0 into that mix. Obviously, it won't change the number, but it does impact the total probability. Standard deviation. Let's move on to a new color. We'll go to blue. We are not calculating standard deviation by hand. I'm on slide 16, by the way. But what we need to remember is that standard deviation is the average distance of an outcome away from the mean, okay? Something I want to be very clear to you. When you see the word typical value on the AP exam or on my tests, that means within one standard deviation of the mean. So the key here to recognize is that 100% of typical values are within one standard deviation of the mean. In some of the classes that I ran with, I used a question that had some answers that were trickily worded. So something I want to be very clear about is they can say a typical value sits in the middle 68%. What you can't say is that a typical value sits there 68% of the time. It'll sit within the middle 68% 100% of the time. But just to be careful on wording, typical values sit within one standard deviation of the mean to the left or to the right. And remember that standard deviation is shown as this little blueberry. Oh, that blueberry was so ugly. This is some wonderful review from the past. But look, it's finally in blue, quite by serendipity. So that's our standard deviation. We know it's a measure of spread, so how far apart the values are in our graph, our distribution. and it's the average distance of an outcome away from the mean. Very important. So typical values within one standard deviation of the mean. Moving on to slide 17, variance. All you need to know for today is that variance is equal to standard deviation squared. That's all you need to know. That's all you need to know for now. And just know that it will be important next class, and that variance is also a measure of spread. And actually, as you will learn next class, variance is actually more honest in terms of its utility. We simplify variance in a very particular way, or at least we calculate it or use it in a very particular way to calculate standard deviation. But variance in a lot of ways is more fidelitous to the raw data, and we'll see why that's useful in the future. Okay, for standard deviation, I give you a way to write. If it says interpret standard deviation, you will say, as it says on the slides, a randomly selected value, in this case I use student scores, will typically, and this is so important, differ. Again, the second I use the word typically, I mean the middle 68%. From the mean, you will then state the mean. Then you will say by blank units. Mind you, this is all you have to say. You don't have to say middle 68 at all. So I want to be clear. Don't get complicated with it. Don't walk yourself into a back corner. But a randomly selected value will typically differ from the mean of blank by blank units. So that means if you were to pick a typical value, it should sit within one standard deviation of the mean. Your typical value is in the middle 68%. Okay? It is in that 100% of the time. Moving ever forward. Sorry that I feel the need to nail that one home so much, but I got some good questions about it after school, so I wanted to make it abundantly clear. Just one of the times where AP will give you different options, and you're like, wait, which one's the right one? Just make sure you're sticking with the truest definition, and then AP can do whatever they're going to do. Again, they live alone. They don't have love in their life. Their families are empty, and they don't know the wonders that I know in being able to teach all of you every day. Okay, on slide 19, we have more examples. It says to interpret a standard deviation of 0.92, you should be able to do that relatively easily if you randomly selected a typical car, right? From the, car, that's a later question. Or an earlier one? An earlier one. If you were to randomly select a typical student score on the AP exam, it would differ from the mean of 3.64 by 0.92 units. And what's the variance? It would be 0.92 squared, which is like 0.84 or something. No, 0.814? Something like that. Don't quote me on that, but you know where I'm going. Okay, we're on to 20. Slide 20, I just remind you, we've moved off of discrete variables. Discrete variables were things like, for example, the value of a score you would get on an AP exam, right? A 1, a 2, a 3, or 4, and a 5. You can't actually get a 3. Now, mind you, I say this in earlier slides, but remember, you do not need an integer for your mean. Even if you're measuring something like an AP score, which is in its very essence a discrete variable, you could still have means, and you will probably have a mean that is a decimal, and that's totally fine. Excuse me, in the same way that like the probabilities for discrete variables are all decimals. It's totally fine. Continuous variables have infinitely many possibilities. I make that very clear, and I give you some examples. Height, weight, amount of sugar in an orange, and time required to run a mile. Moving over to green. Now I have this fun problem for you where you use standard normal calculations. You should see our normal notation. N is 64. Our mean, and 2.7 is our standard deviation. You should use normal CDF. Oh, I think I can do this. Normal, I'm going to write it backwards because I was silly. Normal CDF. And you'll put in your notation. Your lower will be 68. Your upper will be 70. Your mean, of course, will be 64. And your standard deviation will be 2.7. Right? And what that's going to do is find out what probability there is of a value sitting between 68 and 70 inches, specifically on a normal curve. And the probability you should get is 0.056, I believe, or 5.6%, which means, to be very clear, that means if you look at the normal curve, 5.6% of values. Now, these I happen to know just looking at my mean of 64. I happen to notice that 68 is 1.5 standard deviations away from the mean. So again, if this is 1 standard deviation, that would get me to 66.7. And then we're over here at 68, which is almost 2 standard deviations away from the mean. And then 70, which is over 2 standard deviations from the mean. So if this is 2 standard deviations, then 70 is here. And all this is saying is, hey, this represents about 5.6% of all the values you could conceivably get going through this normal curve. Okay. And if it said to interpret that or to explain that, all you would say is, about 5.6% of values, if you were to, measure the height of many, many, many women over a period of time, the probability that a woman would be between 64 and 70 inches is about 0.056, or 5.6% of your values will sit between those two measurements. Okay. And you will note, because, a typical value is within 1 standard deviation to the left or to the right of the mean, you would say that any woman who is in the range of 68 to 70 inches is not typical per your graph. Okay. So we then have a problem, part 3, where you go through and you're running different mile times. And I will spoil it for you. You should pause the video now so you can solve this. So this is on slide 22. Take a second and pause the video. All right, taking a swig from my vitamin water. I hope that was a good pause the video moment, as it were, and that you solved it well. My question just says, runner 3 thinks he can run a mile in less than 4.2 minutes. Is this likely to happen? I'm going to go ahead and I'm going to tell you that, of course, we're going to use normal CDF. So I'll do normal CDF. Runner 3, I notice, happens to have a mean of 4.5. with a standard deviation denoted of 0.14. Right? And then it says, what are his odds of getting a 4.2 minute race in the next race? So that's my data point X. So I'll make that my upper. Now I'm aware that this is a running time situation. So in terms of the normal curve, lower values are stronger race values. Which is just to say that these are faster times. But we're still going to run it like normal, where my lower will be like negative 100,000, or of course it can go lower even than that. That's totally fine. And we calculate it. And what we should find is that runner 3 cannot run this very likely. I think it's like a z-score of like 2.1 is like the z-score. Right? And so when I run that and find the small percentage of people that sit in that, or small percentage of races that sit in there, it should be a very, very, very small value. And so what I will say is it likely to happen? It is not likely to happen. Why is it not likely to happen? Because if you were to have runner 3 run many, 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 many races, and you were to distribute those races on a curve, well, actually, to clarify, you don't even have to say that. You can just say if runner 3 would run many, 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 many races, only about blank percent of them would be 4.2 minutes or less, or the probability that he would run a 4.2 minute race or faster is blah, right? And any of those would be fair ways to go about it, right? And you could just turn the z-score of 2.1 into a percentile. I'll just check that. Actually, the z-score is negative 2.1, I should say. So I'm going to just grab the percentile. I don't have my trusty TI-84 calculator. I deserve any horror that I feel in this moment. And believe me, I do feel so much sadness, so much horror. How could I have forgotten my oldest friend, who I always tell you to show love to never forget? All right, 98.2% of values are less than this or greater than this in this case, right? So you only have like 1 to 2%. So you should have gotten something like 1 to 2%. 1.78 is what I'm getting here, something like that. Okay, we're on to slide 23. We have another problem. We went over these ones in class, right? But these are all on your practice sheets. And you can, as always, shoot me a reminder if you want me to go through any of these. But I would recommend for the three black card problem, you go through and you run a probability tree and then just run your probabilities here. There is an exit ticket and AP problem that I will post up that I will give you a chance to work on as well as some other in-class problems that you can practice, like slide 27. It has an egg problem. And then slide 28 has some extra problems from the classwork. We will be going over those in class next class, and I expect those done. But I am so proud of you. I thank you so much for hopping on and talking probability with me. Remember, this is the point in the year where things kick up in first gear, right? We are going to be driving. Well, wait, no, not first gear. First gear is like the slowest gear. What am I talking about? I'm a gearhead and I'm giving a wrong metaphor. Things are about to pop up into 12th gear, but you are ready for it. And I am here with you every step of the way. Put the work in, study along and along. Remember my story and stay with me on this. I love you. I'm proud of you. And we're going to roll ever forward. This is Mr. Mays signing off.